welcome to the webinar today. As kindly introduced by Laurent, I am Giorgio, and I will be presenting to you today our adoption of model-based system engineering and software engineering too in our student society developing aerospace projects. So today, the presentation will be split into three main sections. First, there will be a brief introduction about who we are, what we do, and the kind of system that we approach. Then we'll talk about our experience adopting model-based system engineering techniques, specifically the motivations, tools, the processes, and finally some of the lessons learned. And finally, we'll have quite a beefy section covering our method for bridging the gap from high-level system engineering to lower-level software development targeting embedded systems. Finally, there will be the usual 10 minutes or hopefully maybe even 15 for Q&A. So who are we and what do we do? We come from the University of Glasgow in beautiful Scotland, UK. And we are a student-run society that specializes in CubeSat development. We were founded in 2019, and in the mostly 5 years that we've been around, we've accumulated a good team of students, mostly undergraduates. Some PhD students are around, but they don't really do a lot of the leadership, and there's no kind of uni staff doing the leadership. So we kind of just have to figure out everything on our own. We take good pride in the diversity of our team. We're the more or less 80, the numbers fluctuate, but that's the kind of average from about 20 countries. It's a very nice international setting. And also we study a number of different disciplines. There's people from all sorts of kinds of engineering and also outside of engineering too. We have within STEM and also outside STEM, business, even psychology and law, because those are important aspects too. What do we do together all this time? We focus on nanosatellite development. Developing basically very, very tiny satellites about the size of a milk carton, like the one that's shown in the CAD model on the right. And we do this basing our work on three pillars. The first is the demonstration of new technology, because we want to try and push the boundaries of what is possible on Earth and in space. But it's 2024, and that's not really enough anymore to justify a CubeSat mission. So we also do it to collect data for an actual application that brings some value to some actor around. And also because we want to squeeze as much fun as we can out of this engineering process, we try our best to develop all the subsystems, or as many as we can, in-house, as opposed to just buying them pre-made, because then we get to experience the full life cycle of engineering, from design to implementation to integration, instead of just design and integration of cost components. So what are these technologies that we want to demonstrate? The first is machine learning, especially on the onboard side. We'll talk about the application in a second, but we take some imagery and then we want to process it on board so that we don't need to do as much work. For example, downlinking the data to the ground and then not so much processing on the ground, so that our whole kind of system can be quicker to spit out the data that we want. Another technology that we are interested in developing and demonstrating is kind of more mechanical and is about the deployable drag sail. If you're in the space industry, you definitely are very familiar with why we want this kind of thing. If you're not, just know that there's a lot of space junk in orbit, namely satellites that are out of commission, that are just done with their mission and are just sitting there. So new regulations are in place from ESA, NASA, whoever, recommending very warmly for new missions to have some means of deorbiting the spacecraft quickly after end of operations. What is this operation? Is so it's something based on Earth observation. So no, not really communication, because that's kind of more commercial, and definitely something around the Earth. And specifically, it's about assessing the risk of wildfires in area. So our idea is to take pictures and then identify the moisture of plants, and then from that identify the likelihood of a wildfire occurring, and from some other land-based data, identifying the severity of the impact of a wildfire in that area. We also have a spin-off mission. If you're from the UK, you maybe have heard of from this mission. It uses very similar technology because it used to be the same people from our team that started it. But for a slightly different application, which is more about monitoring the evolution of coastlines on the UK. This has a difference that it uses mostly commercial off-the-shelf subsystems, because they needed them way quicker, and also because they won £600,000 from the UK government for a competition looking for a student team to actually launch their satellite. And currently, they're doing very well. They're in their phase D, doing the integration, I believe, right now, and they'll be moving into testing soon. Also, we do some research and development, and we try to have a relatively stable presence at conferences around. We started from a couple of years ago, one paper at SSEA. Then last year we had two papers. One of them, the first one here, is going to be the one that will be discussed thoroughly in the third section today. And also we have three papers that we are planning on presenting at this year's IAC that will take place in Milan. So if you're in the industry and you're going, pop by and say hello when the time comes. Of course, then there's how we do it. And so everybody, of course, is here for the model-based approaches that we apply to both systems engineering, mostly with the functional paradigm using Capella, because that's just what Capella does. But also we have some projects using a kind of more numerical approach, but this is beyond the scope of today's discussion. Also, we do this for the software engineering, especially for our embedded systems. And this is where taste, the kind of second part of the model-based stack that we use, comes in. And of course, we'll be talking much more about this later on. But also, there's something else about how we do our work. And it's the kind of agile approach. We've taken a page out of the software engineering book. If you're in the industry, again, you know this. But because we are students and want to get a thorough experience, we approach our work in these kind of 2-year-long sprints. And at the end of each, we try to have a sounding balloon mission to put our work in a real life context. We do this because, very differently from kind of normal companies, we're a student society and we're students. So we graduate at the end of our uni experience. And so that means effectively that we have a very fast and very forced turnover of experienced members. They usually get 2 to 3 years of valuable contribution in the society. And then they just have to graduate and move on. So we still want to get a consistent experience of the full life cycle of engineering. We don't want to have some students just doing the design, and then a couple of years later, some students just doing the implementation, and then some years later, some students just doing the testing. We want everyone to experience a little bit of everything. And also, we want to be able to validate our work, because we don't want to do something for 3 years straight and then not know if it works at all. So this is something that we just started last year. And this was the mission CloudView that you see in the balloon on the right, where we put 3 subsystems of our own development in this box that we strapped to a balloon and sent it in the stratosphere for 3 hours, reaching up to 35 kilometers and working very nicely. We'll have some more about this at the very end for our validation. So now let's talk a bit about our adoption of model-based approaches, our motivation, the tools that we've picked, and how we use them, and what have we figured out from the couple of years of trying to use these tools. So first, why? Again, this comes from this main point of having a fast and forced turnover of members due to graduations, because of course students just want to move on and get a job that actually pays. And when we were using document-based system engineering approach, it was okay, but let's say that the documents were a little student grade in quality. And of course, some were like this, but some were also really, really good. But anyway, for any kind of quality of the documents, the compliance just remains kind of voluntary, right? As in, there's not really anything binding you to reading and understanding and applying the contents of this document that was written before you. So what we had in practice was that teams were often starting over from scratch, just throwing away all the work that was done before because they either didn't know it was there or they didn't understand what it meant or they didn't understand why it was that way. And so maybe they thought that they could do it better. And starting over, there's no guarantee that the work is going to go further than the one done before, or even go in the same direction as the one done before, or even be consistent with the idea of the whole system seen before. So that's a really big problem when designing complex systems with different subsystems integrating with each other, right? So of course we could have tried to solve that problem by putting in place a very thorough and very formal kind of handover process and recruitment and training process. But we already have so little time in this project because of the fast and forced turnover issue. And we didn't really want to spend it doing boring bureaucracy, right? So instead we figured, what if there was a way to just enforce this? And we found this in model-based approach. And of course, after we started doing this, all the work is still by definition, of course, student grade, because we are students and that's what we do. But at least we get the very important aspect of enforcing the consistency. If you're in Capella and you need to do some new work in the same model, you need it to be consistent with the work that's already there, unless you just delete everything. But that's a much more conscious throwing away previous work than just not reading a document. And this way, we found that teams were very consistently progressing instead of just starting over because they had a clear foundation to work on every time and a clear outline of what to develop and how to develop it and what are the constraints that they need to develop it in. So what tools do we use to get this nice upgrade? Of course, we use Capella for our systems engineering. As you all probably know, it's developed by Thales and Obeo, the very kind hosts of today's webinar. And it's, of course, free and open source, go open source. And very importantly, it implements the Arcadia method, which we'll cover a bit shortly the advantage of, but in a pinch, it's really helpful to have it integrated into the tool for guidance as we are students. So we obviously like that. Then the other half of our stack is taste. And this is something a little more exotic. It's a toolchain developed by the European Space Agency together with multiple partners from industry under ESA contracts. It's also quite surprisingly, because it's very powerful, free and open source, just like Capella. And it targets heterogeneous systems. So that means systems where you have multiple blocks of code that are written in multiple languages and they're deployed on multiple hardware nodes of different architectures. Also, it supports formal verification, which if you know, you also know why it's so great. If you don't know, we'll cover it later on, but it's basically testing but supercharged. It's like proving a theorem about the property of your code that then if it's proved in the end, you know with mathematical soundness it's always going to be there because all the possibilities have been exhausted. Now, the free and open source points are important in both cases. because again, we are a student society. We don't really have a way of bringing in revenue, right? So the free aspect was definitely something that drew us to both tools in the first place. But now that we've started using them and that we've found such great successes using them, as we'll talk about in a second, we definitely wouldn't change them for any other paid option. However, still, if you aren't offering a paid alternative to these tools and want to show your support to us, because maybe you like what you're seeing and want to have your name on like our t-shirts or whatever, definitely shoot us an email or a message, and we'll be in touch. Okay, so after the ad break, how have we been doing our work? Of course, there's a lot of knowledge acquisition because we're students. We're at uni to learn, so that means that we don't know how to do things. It's a good thing, therefore, that both tools have such good training materials, both tutorials, documentations, videos for everything. And in both cases, also the people behind them are really, really nice and very available to explaining how things work and getting you on board to the tool. This is what we got with the with training courses. We got them both from Thales for Capella and from Isa for Taste. And these were the things that really changed it for us. We started from the kind of self-learning, but this is where it really turned for a lot of people, because of course, just having someone who is experienced in the field tell you all about it really helps out massively. But also, there's a lot of transfer of knowledge among ourselves, and we do this by taking another page out of the software engineering book, and it's the pair and mob sessions. If you're in the industry, you know how this works. But just to refresh, it's where you have one or more navigators, and this is usually the more experienced person or experienced people, and they can't do anything. They can only talk, but not write anything on the keyboard or touch the mouse or do anything to the computer. The only one that can do anything is the inexperienced driver that kind of gets radio commanded into doing what the more experienced people think they should do. And we've applied this both to the modeling at the kind of higher level of systems engineering, and of course also to the classic application of programming for our embedded software. Also, we have adopted an interesting, in our opinion, way of doing model development, which is the kind of concurrent engineering philosophy, where people from different disciplines come together to decide on the design of the system. And this really fosters the collaboration between different disciplines of students doing different degrees, which is very helpful because what we know somebody else doesn't, and what we don't know somebody else does. Also, we have some very particular process for software development, and this is the bridge method that we'll cover in the next section, that kind of bridges together Capella and Taste to merge high-level system engineering and lower-level software development. So, what have we learned from this experience? There's a first point that's very interesting to us, and it's that model-based approaches can actually be helpful in learning system engineering as a whole. In my experience, I didn't know system engineering at all before encountering Capella. And I kind of learned it by learning Capella at the same time. And I found that the integration between method and tool was really helpful in this. I had no idea about like where to start with the requirements and the system design. And having this integrated into the tool was really helpful. For example, in it telling you to start with not even the requirements, but the context, the environment around your system at the operational level. And then doing all these activities at that level, and then moving on to the system architecture and doing those activities again was really helpful for kind of drilling that process into my mind and that kind of way of thinking. Also, we found that the pair, or even better, mob modeling together with concurrent engineering can give birth to a really interesting combination of knowledge transfers, both on the side of the method itself, so how to do system engineering as a whole, how to do it in a model-based fashion, and how to apply the specific Arcadia method to this problem that you're analyzing. Also, of course, on the knowledge of how to use the tool, just what button to press to do something. It starts from there, and then the kind of pair modeling moves on to more complex instructions, like make this functional chain instead. But also, very critically, there's a lot of exchange of knowledge about the system itself that happens, which is really interesting because it's elicited by these other things. Like you have to, for example, break down this function at the new level, and so you need to know what lower level steps are needed to perform the higher level function. And this is something that from your discipline you might not know. So that's where you ask somebody else from another discipline to enlighten you. And it is actually very enlightening in my experience. I've learned a lot, and I've heard from a lot of friends in the society that they've also learned a lot from just the elicitation of this exchange from Capella itself. Okay, so now we've talked about who we are and what we do and why and how we do it. So now it's time to talk about the exact specifics of this particular method that we've devised to bridge the gap from higher level system engineering to lower level software development. We'll talk about the nature of the gap and also the precedent works that have been carried out to try and bridge the same gap. Also, the tools and workflows, a bit more into the specific of those, and then finally how it all works step by step. So the big problem with system engineering is that the only thing that you get out of it is the specification and not the actual system. It would be very nice to get the actual system, but turns out that especially in the context of software, it's not so outlandish to think that you can actually get the entire system. Of course, it's harder in the context of more physical, mechanical things because manufacturing is just way harder. But software doesn't really need to be manufactured in the same way as physical things. So it's not so outlandish to dream of a world where you can actually get your real system out of the system engineering phase. Usually, yeah, you just get the spec for manual implementation, but this is a process that can have faults in it, usually because it's done by a human. So we're all fallible and we can all sneak in bugs, even if the design is perfect, or the design can just be wrong as well. So wouldn't it be better if you could actually get something that can just execute straight up? And to be honest, we haven't been the first to think about this issue. Some tools do exist that attempt and possibly even succeed in bridging this gap. But to be honest, I don't really know if they do succeed because they're proprietary and they're commercial and they're expensive. And also they're outside of the Capella ecosystem. And we like Capella so much that we wanted to see if we could stay within the ecosystem so that we could keep the same kind of mindset and reasoning. But also there has been one very notable and very inspirational, to be honest, instance in which this has been done in both an open source way and within the Capella ecosystem. And it's the work by Polish company N7 Space. If you've been browsing around the Capella add-ons page, you may have encountered this this plugin screenshot on the right, the Capella Taste plugin, that is going to sound like exactly what we wanted. And to be honest, it does exactly what we wanted. It takes in a Capella physical level model, and it spits out some taste model that can get turned into code. This was developed in 2020 by this company N7 Space from Poland under a contract by the European Space Agency. Unfortunately, there hasn't been any further contracts by ESA on the maintenance of this tool after the kind of proof of concept stage. So there hasn't, of course, been any free maintenance of this when people have to feed their families. So there has been ever since a divergence of the internals of both tools. Both Capella and Taste have moved on with their versions and their internal architectures, of course, to try and improve the software. So the result is that this very, very interesting and inspirational tool is kind of stuck in 2020 versions of both. And since we started after this, we used Capella 6.0 for our model. This wasn't really compatible with our model, and we would have had either to start from scratch with the model or to just make another add-on similar to this. So the second option is the one that we evaluated as preferable in the end, and we stayed faithful to the same tools. So we picked again Capella and Taste to try and bridge this gap again, because it had been done already once in such a successful way. The only problem being time. So why change anything? We use Capella for the higher level side of it, which implements the Arcadia workflow, which, as you know, includes 4 main levels. Starts with the operational level, where we specify the context and the environment the system is going to be operating in. Then there's a system level, and here on the right, you're going to see just decorative screenshots of our system diagrams at these levels, where you just see at this level the system as a black box. Then there's a logical level where you see the system as a kind of gray box, seeing the subsystems inside, but not kind of all the way down. And then finally, there's a physical level where you see it as a white box throughout its whole depth. You can discern all the components, software, hardware, and whatnot, down to the tiniest thing. Also, there are some important transverse models included by Capella that are particularly critical to our method. And these are the finite state machine models, where you just model your system as a set of states and transitions between states and triggers that trigger these transitions from the state and effects for each transition. And also the class diagram that just represents the relationships between classes of data, fundamentally. The other half is, again, Taste. If you're not familiar with this one, because it's a little more exotic, it uses its own kind of workflow, but in a similar way, it's also very strongly model-based. And indeed, it has 3 views where the user specifies this consistent model throughout them. The first one is the data view, where we specify the data types for use throughout the system. So any hardware node of any architecture running any software block of any language is going to be able to have access to all these data types, regardless of all these variables stated before. Then there's the interface view, where we specify the software components in the system and the interfaces that allow data to be exchanged between them. And then finally, there's the deployment view, where we specify the hardware components of the system, and we allocate the software components to the hardware components and the software interfaces to the hardware links. Now, if you've been following these previous walkthroughs for both tools workflows, you will have already picked up quite some similarities, and that's also what we did when learning them. And we figured that we wanted to definitely make the most out of these similarities, and we saw some opportunity to go beyond the the work that had been done previously by the previous plugin. And because that had to also be implemented while we had no such claim, we thought that we could expand on it. The main thing, the main goal that we had in mind was also future proofing, because all the work that they did before was great, amazing, but evidently it didn't withstand the test of time without further funding, which is only reasonable. But we had zero funding in that sense. So if we did the same, there would be even lower of a chance of it withstanding the test of time. So that's why we figured that we should start from just outlining a theoretical foundation for the semantics of this bridge, starting from the mappings between entities and relationships and the activities to be done to bridge this gap. And then only as a follow-up work, doing the automation of these activities and formalization of those mappings. So that if the internals of the tools changed again, then there wouldn't be the same problem of kind of coupling, but the semantics would just be there standalone, uncoupled from any of the internals of any tool. And if they change, they can just be re-implemented. So let's talk about these mappings between entities and relationships are the kind of groundwork of this method. Again, if you've seen the previous diagrams, you may have picked up on some symmetries between the two, the semantics of the two tools. But here on screen, you're seeing the our proposed mappings of entities between the physical level of Capella, because of course that's the lowest to an actual implementation. So that's the one that makes most sense to be bridging, and taste. So for example, we're not going to walk through the whole table because it's a little long, and there's another that's just as long. But for example, in a Capella physical architecture, there are some behavior physical components and node physical components that represent respectively kind of more software things and hardware things. And so they are also nested. So of course, the leaf, for example, of a behavior physical component is one of the software components in taste. And then a group of those is just going to be a group of those also in taste, because that allows nesting too. And the highest level behavior physical component in Capella is going to translate to a partition, because the software components belong within a partition. And similarly, at the bottom level of a hardware component, that is a device that runs some software, a hardware device that runs some software. And then you can also go higher up in this nesting to represent hardware modules that kind of carry devices, and even broader hardware boards that carry different modules or contain different modules that have different devices. And this is this one specifically is the main way that this method can also extend a little beyond just software on its own, and into the kind of realm of more electronic based embedded systems. That's not the focus of the method. So of course, all the rest of things just pertain exclusively to software. But if you just allocate functions to behaviors that are not going to be representing in software, you can also represent just hardware devices, ASICs, FPGAs, or whatnot. So entities are tied together by relationships, and so we've also mapped those together. So for example, in the very simple example that we were talking about just now, the behavior physical components representing software components are allocated to node physical components representing hardware nodes. So in the same way that allocation in Capella is the deployment of a partition or a function, that's the name of taste software components, to a hardware node. And very similarly, the allocation of component exchange between two different behavior physical components to a physical link is also represented in taste by the deployment of a software interface to a hardware link. Now, of course, these are going to be a little foggy right now, so we are going to be illustrating them very shortly. And we're going to do this by basically diagram comparisons. We have come up with two different classes of mappings. One is a mapping of implementation diagrams. So these are the diagrams that you will be looking at while implementing your system from Capella into taste. And then also there's a mapping of verification and validation diagrams. So these are the diagrams that you'll be looking at while verifying and validating your system to see if you've built the right system and you've built the system right. So all these different mappings and activities come together in this V-shaped workflow that spans the whole kind of engineering lifecycle, from design to implementation to verification and finally validation throughout both tools. So it starts from the high level system level in Capella, then into the logical level in Capella, and then at the physical level, that's where the actual bridging occurs between Capella and taste. And then, of course, it goes back up to higher levels of abstraction to do higher level verification and validation up to like acceptance testing. So we're going to start explaining bit by bit these activities, and we're going to do this taking a look at a case study of a simple feature that represents the area of interest management for our spacecraft. Remember that our mission is Earth observation, so we want to be taking pictures of the Earth, but we don't want to be taking pictures of the whole Earth. We're not like Google Maps, and we definitely don't have the same means. So we want to have some way to be able to configure areas of interest to add or overwrite new ones and enable or disable those that we want or don't want. And we want to be able to trigger the system's imaging mode when the system is inside an area of interest, and trigger a non-imaging mode when the system is not inside of an area of interest. So this is the kind of top level feature that we wanted from our system, and that we'll be illustrating the method with in a second. So it all starts, of course, from the beginning of the V-shape in the Capella system level. And this is just the usual Capella and Arcadia method at this level. So you identify the functions for the system to perform, you allocate them to the system or to actors. And also we definitely do recommend that you should tie them together with functional chains, because those are very prevalent drivers of the design methodology and also the verification particularly. We haven't showed all the diagrams because that would definitely be too much, but you can find them at a link in the last slide that has the HTML export of our whole model. So you can, go through all of it in any amount of depth that you want. Also, of course, you can start higher up at the operational level, but that's just beyond the scope of the system itself, so we haven't included it. Then, of course, after the system level, there's the logical level, where also you do the same exact thing. You break down the functions, you allocate them to subsystems, you tie them together with exchanges and functional chains. Then again, there's the physical level, where once again, you do the very same thing. You break them down into physical function. You allocate them to the software components. You allocate the software components to the hardware components. You do the functional chains and whatnot. And then finally, after that part, after quite a thorough physical level, this is where we start actually bridging the gap between Capella and Taste. So this is the first kind of comparison, and it starts from a class diagram in Capella that represents the data to be exchanged as part of the interfaces in the model. And this we can just translate into the Taste data view because it represents the same thing, right? They're both representations of the data throughout the system. So we start from the basic data types highlighted here. And then we can move on to the more complex data structures that are kind of aggregate of the basic data types. And then we have our data view in Taste, and we have and we know the data types to be exchanged throughout the system, and we've specified them for all the components to use. Next, there's the specification of these components. So again, it starts from a Capella interface view, which is very aptly named because it maps to the exactly identically named view in Taste. So we again start by just specifying the components that need to be here. And then also, if we want to be nesting components, we can also be nesting them in component groups in both tools to have a tidy system. Then we connect the components with interfaces according to the specification in Capella, kind of driven by the creation of component exchanges from functional exchanges crossing the boundaries between different behavior PCs. Then once we've done that, we can also, okay, I think this is, no, I'm going up, sorry. After the specification of the interfaces themselves, we also allocate the exchange items to them. And this maps to specifying what is the data type of the data exchange as part of the interface in Taste. So again, we just do the same following the specification in Capella. You know, these are the same data types that we specified just a second before in the other diagram. And very similarly in Taste, we do this by specifying one of the data types from the data view. In Taste, this happens in a pop-up window. That's why it's not shown, because it's not very interesting graphically, but it just shows up if you double-click on the interface. Then there's the last bit, which is allocating the software to the hardware. And this is typically done in a Capella physical architecture diagram. So we start from one of these, and you'll see from this diagram that it doesn't have any of the functions because we just don't care about them in here. So that's the view that we recommend starting from, because otherwise you're going to have a lot of physical functions probably, but they're not the focus in this diagram. And again, we start by creating the hardware components that we need, one for each node PC. And then we move on to allocating the software components that we defined in the previous diagram to these newly created hardware nodes. Then, of course, similarly to the last step of the previous diagram, we also connect the hardware components through a hardware link, and also we allocate the connections in the software domain to this connection in the hardware domain. Again, that's something that in Taste on the right is done through a pop-up window, but it's much the same. It's a choice, a selection of the interfaces that cross the boundary between the two hardware nodes, and that represents the exact same thing from Capella. So this is the point where we start to go beyond the kind of previous work in the previous bridge plugin, because we've specified the architecture of our system now, but it doesn't do anything. We haven't written any logic just yet, right? So this is where we start writing the logic, and we do this starting from a finite state machine in Capella. Capella lets us associate a finite state machine to each of the software components, and taste very nicely lets us develop the logic for those components in a language called SDL that's based on finite state machines. So we start, we go transition by transition, and we start from the initial transition. Of course, we specify the initial state, and then of course, this one doesn't have any triggers, so we just specify some effects as allocated to the transition in Capella. And then we specify the target state. Then we move on to the next transition. We specify, again, the starting state. This one is not an initial transition, so it has a trigger. Also, Capella lets us allocate exchanges or functions as triggers to transitions. So we see that before the slash here, and we just translate it to the exact same exchange in taste. Then we have the main body where the effects are performed of this transition. And then we have the final, the target state for this transition. We have another transition, and we do much the same: initial state, trigger, effects, final state. We have a fourth and last transition, and again, it's the same process: starting state, trigger, effects, final state. Now, if you do this for every one of your software components, then you basically have all the behavior set for your system. So now it's time to actually figure out whether they represent what you want the system to do in the first place. So as you've seen here, the view that taste gives you when writing this code is slightly different from the finite state machine. But it also offers one that's much the same so that you can compare them. So on the view on the right is state chart view auto-generated by taste based on this previous view on the right. And this you just compare to the previous diagram in Capella, your state machine from Capella. So you see that you have the same number and names of the states that represent the same things. You have the same transitions. The transitions have the same triggers. Unfortunately, the effects are not shown, but this is probably enough to identify that this is a decent enough match to be considered valid or verified, I should say. And after you verified all your units, you also want to verify how they kind of integrate and interact with each other. So you do this, but this representation in Capella would be an exchange scenario, and taste very, very nicely allows you to get exchange scenario that are called message sequence charts in ITUT standard from your executions, or alternatively, you can write a message sequence chart and have it be executed as a test case. And again, this is basically just the same thing down to even, down to even the states. So we compare them just one-to-one. In this case, the message sequence chart on the right is like 3 separate instances and different test cases of the same kind of test. So there's these 3, but they both have the same components involved, and they both match the states, the kind of fixture states at the beginning and at the end of the test, and they also match all this first exchange. This is an optional exchange, so only 2 of the 3 instances have it, but it also matches where it's present. Then there's another old case, so only 1 of the 3 instances matches, but where it's present, it also is a match. And then finally, all the 3 have the last exchange. So these are also a pretty evident match between them. And then finally, there's one last thing that is basically a different representation of the same information contained in the last diagram, but in a way that focuses more on the architectural impact of these exchanges. So this is basically the same as a physical architecture with highlighted functional chains. And it's good for showing the presence or absence of side effects on components. So these are the components involved. They're the same components involved in the functional chain. And these are the same exchanges involved in a functional chain. You can kind of trace the highlighted arrows here in much the same way. And these are the components that are not involved in this exchange, and indeed they are not even present in the Capella diagram. This can also be, these two last activities can also be extended to the higher levels, but that's a little too much, and we're running a little late, so we'll skip them. But they're just done by removing from your diagrams all the exchanges that don't cross the boundaries between entities at that level, and including other entities at that level, but only in the extent to which they have boundary crossing exchanges. Finally, the last bit, after you know that you've developed the system the right way, so according to spec, is whether you've built the right system, so whether it actually does what you want it to do. And that's the last chapter in our story too. We put all our subsystem in this styrofoam box, and we strapped it to a balloon, and we sent it to the stratosphere. And honestly, to our surprise, it just worked very nicely for the 3 hours and 35 kilometers that we were saying at the beginning. And we got some very nice pictures of Scotland, like this one. The colors are a little weird because it's near infrared instead of red, and it's mostly covered by clouds because, again, it's Scotland. But if you squint really hard, you can see a tiny lake and a small river in the lower part of the picture. And we got like 100 more of these, and they're mostly all clouds. But we got the pictures, which was the point of our mission, to validate that the subsystems did work, and the whole system did work without any fault for the whole duration. So what did we get out of this? Very briefly, there's a shift of the implementation and activities into the design model, which is very helpful for a more thorough system analysis, but also very helpful to debug issues in the actual system. We can talk more about this in the very brief question time, but we had a very nasty async bug that this method really helped massively in debugging. And most importantly, it just works. We put our stuff on a balloon and it worked. So for us, that's really the main takeout here. Of course, nothing is perfect. So this is still all manual, and it's very time consuming. But also, most importantly, it's an entry point for bugs, because we're all human and fallible and we make mistakes. This, of course, is by design because we wanted to start from this theoretical foundation. But as the fine folks from N7 have done in the past, we think that it can be applied in the same way to our method to be automated in both the implementations and verifications. Also, finally, there's a little shortcoming that this method only has the verification of component behaviors at the lowest level. And we think it could be very interesting. Yeah, if you seen the diagram, there's 3 blue lines only at the bottom level and none at the higher ups. And we think it would be interesting to use Taste's formal verification capabilities to move this up to both the subsystem and the system level, to catch some of the sneakier bugs that can make their way into the system. Sorry for running a little late, but thank you very much for your attention. And we have some time for questions. If they can't be answered, feel free to shoot them anyway, and I'll reply to them in writing.
Okay, first of all, before we move to the questions, I really want publicly to thank you for the hard work you've put in your presentation, Giorgio. It is very clear
thank
that
you.
it is
thank
the
you very
result
much.
of huge work, and it is top quality, very sincerely. It's
thank
awesome.
you very much.
So I'm really glad we had this great presentation today. So now, it's time for the questions, and I think everybody is just gathering their minds to find some question to ask, but everything is so crystal clear that there are no
Thank you very much.
so far. So I'm just curious about how your student society is organized. How many women and men do you have in proportion? And well, how do you manage each year? Because I assume that you have a certain percentage of students moving out and new students moving in. So I guess the students that are in the last year are the guides to the newcomers. And is it successful in getting newcomers every year?
You know, the recruitment process is a little different year by year, because the you know, pool of students that join is a little different year by year. But we've managed to get on the kind of gender equality issue, I believe, quite a good stance. I'm honestly not sure about the exact numbers, but off the top of my head, I would say that it's probably a little better than like the industry average, especially in the leadership positions. A lot of our team leads are women, and it's just really nice to get this breath of fresh air for maybe some students that have been into some companies that don't have as nice of a diversity, and kind of come back and can enjoy some of it here. The leaving issue. Sorry,
sorry for the interruption, Giorgio. We have a few questions, so
of course,
I think we should directly go to them. So first question is, the question is, you used MSP 430. What other platforms are you interested in?
Correct. Thank you very much, Mikhail, for the question. And thank you very much also for the help that you provided with us using this one platform. We are also interested in STM-based platforms, namely because they have a little more memory than MSP 430. But also we've been interested in some of the front-grade Geisler platforms, especially for the stages where this is hopefully going into space because of the radiation hardening.
Another question, just I think the answer is going to be very quick, so I'm putting this one first. Are any of your models available somewhere? I think you mentioned the HTML
Yes. Thank you very much for the question. They are available in line with the spirit of open source. We also put the models themselves freely available for anyone, and we've put some links in chat. You can browse the GitHub repository of our model. But if you don't want to download it and unzip it and bring it into your Capella because maybe you have 6.1 or a more recent version or an older version, we also provide a link to the HTML export of our model that you can just browse online from any computer or your phone or any device.
Okay, perfect. Another question now. Did you actually try formal verification of your model in taste?
So I hate to admit it, but unfortunately, we haven't gotten to this part just yet. To be very straight up with you, it's actually one of the main elements that drew us to taste in the first place. Its support for formal verification within embedded systems. But before doing the formal verification, we kind of had something to verify. So until now, we've mostly focused on getting that into existence. But the interest that we have in formal verification is definitely a lot, especially in the automation and formalization of those symmetries between taste and Capella. We think it's one of the key technologies that could allow that step, the step of finite state machine comparison, to be automated and made into something that's actually formal and extensible to the higher levels of abstraction by just combining the states of the subsystems into the state of the system.
Okay, and do you think maybe next year you would have some time to try and
Hopefully, I mean, I'm leaving now because I'm in my last year. So unfortunately, I won't be able to really have the same kind of involvement that I've had in the past. But I would be definitely interested in doing that. It's something that's been bugging me since we started, and it's something that I find really interesting.
Okay, and one last question. We're already late, so I'll just show this one. Did you, and if so, then how, incorporate hardware elements into taste design?
We only really did so to a very low kind of extent. We only really had the one MSP 430 running it, and not really any other hardware nodes, mostly because the other hardware nodes that we had in our actual systems were architectures not really supported by taste. The other, like for example, we had, you saw in the balloon picture, we had the Jetson Nano to run the machine learning pipelines, and that's not supported by taste. So we had to just kind of do the usual software engineering in accordance with the spec outlined in Capella. And that wasn't really nice, but you know, what can we do? Not everything can be instantly supported. So it's nice that it was still successful, but we would have definitely liked to be able to have other things within the taste model.
That's it for today. Thank you all for your attention. Thank you very much, Giorgio, and let's be in touch. Goodbye.